各位同学好 ，Welcome to the course of electromagnetic theory. I'm your lecturer, Professor Wen-Jiao Liao. So, in chapter 1, we basically will review important EM relationship, that is, the Maxwell equations, including the continuity equation that describe the relationship between surface current density and surface charge. And we will also look into important relationship, that is the boundary condition, and in particular the boundary condition on conducting surfaces. So here is the Verdi laws and Ampere-Spatial law, the first two equations of the Maxwell equation. So on the top are the Verdi's law and Ampere-Spatial law in differential form. We know that Maxwell equation can be written in differential form and integral form. For differential form, we are looking into the electrical field, magnetic field intensity, and the source relationship at a particular point. So therefore, when we write differential form, we only look at a specific point and its relationship and the relationship between E and H field at that point. So, for example, in Verdi laws, it says the curl of E equals to the negative of the time derivative of B. E is the electrical field intensity, B is the magnetic flux density. Okay, remember E is the electrical field intensity, H is the magnetic field intensity, while magnetic flux density is paired with D, the electrical flux density. So always on the left hand side you have curl operation. That is one kind of spatial derivative. Okay, so you find the difference of the electrical field distribution in space. In particular, the curl operation is look into the so-called lateral derivative. That is the direction that is not parallel with the direction of electrical field. That is the direction that is perpendicular to the electrical field direction. So in spatial derivative of vectors, we have two kinds of differential operators, the curl operators and the divergence operators. And the curl operator is in the form of cross product, while the divergence operator is in the form of inner product. Okay, so 也就是外积跟内积哈，所以旋度是外积的形式，而散度divergence 散度是内积的形式。它们两个取的空间偏微分，空间微分是看不同的面向。Okay, so the curl operation look into the lateral derivative of the function in space, while the divergence operator look into the difference of the vector along the direction of the vector. So it's also referred as the longitudinal derivative. That is the direction that is parallel to the direction of the vector. Right? So the Faraday's law, the first two equations of the Maxwell equation, they are looking at the lateral derivative, the spatial difference on the sides of the vector. So Verdi laws look into the curl of E, while the Ampere-Spatial law look into the curl of H. Right? And so on the left hand side is the spatial derivative. How about the right-hand side? As you can see here, the right-hand side includes the time derivative of magnetic flux density. For ampere security law, you have the time derivative of electrical flux density. So on the right-hand side, we look into the time derivative of E and H fields, while we also look into the source condition. So here we have the impressed electrical current density of the source. So okay, the next thing we would like to look into is sorry about the background noise. There's so another thing that we look into the Maxwell equation shown here is the field intensity and the flux density are written as a function of position and time. So this is referred as the instantaneous form. So they have dependence in location and time. We usually refer the field intensity and flux density as four-dimensional function. That is, however, it's actually three dimensions in space and 1 dimension in time. Usually, the time and space dependence are decoupled. They are not related. They are independent. So, in following slides, you may see some derivation of the Maxwell equation, and you can see that the derivative of time and differentiation in space, the order of differentiation can be changed because time and space dependence are decoupled, they are independent. Okay, so a more complete expression of field intensity and flux density, all those field parameters should be in the form of space and time. So here we like to try to show that Maxwell equations are coupled. Because some physicists, well, I can write Maxwell equation in just one equation. So we don't need usually when we study in the Maxwell equations textbooks, we see 4 Maxwell equations: the Verdi's law, Amber's Spatial law, Gauss's law of electrical field, Gauss's law of magnetic field. But the physicists say, well, they can be written in just one equation. That's true. It's true, because all 4 Maxwell equations are related. And in the next 2 slides, we can see how they are related. So they are not independent. The 4 equations are not independent. And one historical trivia is about 140 years ago, when Maxwell group proposed the Maxwell equation based on previous experiments of other scientists and his own observation. Originally, there are 20 equations in Maxwell equations, okay, including the constitutive relations and all other equations. And then Hertz and Heaviside reorganized all these equations and provides the present form, okay, a more modern form of the Maxwell equation, about 15 or 20 years later. Okay, so that's the reason why on the textbook you see 4 Maxwell equations. But from my own point of view, I would like to say that the Maxwell equation is actually 5. I would like to add the so-called continuity equation that relate the surface current density with charge density, time derivative of charge density, which is a more convenient way to present the interrelationship between those Maxwell equations. All right, so let's begin with Faraday's law. So here we have Faraday's law in differential form. The curl of E equals to the negative of the time derivative of B. If you take the divergence on both sides, okay, so here we take the divergence on both sides, then the left hand side can goes to 0 because this is the so-called vector identity. It's true for any vectors. So for any vectors, if you take the curl of the vector first, then take the divergence. So you see here we have we take the divergence of the curl of E. It must go to 0. This is true for any vectors. Okay, the divergence of the curl of any vector must equal to 0. So if you take the divergence on both sides, you end up with the left hand side goes to 0. Since the left hand side goes to 0, the right hand side goes to 0 as well. So you can see the divergence of the time derivative of B must equal to 0 as well. Then I'd like to change the I'm sorry. Here we should have a divergence operator in the middle. Okay, so you can change, as I said before, you can change the order of differentiation. You can take the divergence first, the spatial derivative, and then take the time derivative. All right. So the time derivative of the divergence of B goes to 0. And if you integrate both sides with time, then you end up with this relationship. The divergence of B must equal to 0. And this is actually the fourth Maxwell equations, the Gauss's law of magnetic field. The Gauss's law of magnetic field. Okay, so he says that there is no magnetic point source. So for any point in space, the divergence of the magnetic velocity must equal to 0. Okay, so you see here we have the relationship between Faraday's law and Gauss's law of magnetic field, and you can see that magnetic field is somehow related to electrical field. For time variant fields, the electrical field and magnetic field cannot be separated. They are not decoupled. Same principle can be applied to Ampere's-Secchio law. So as you can see here, we have the Ampere's-Secchio law in the small parenthesis. You take the divergence on both sides. So again, the left hand side, the divergence of the curl of H goes to 0. So the right hand side goes to 0 as well. And again, we interchange the order of differentiation. We pull out the time derivative on the outside and do the divergence operation first. So here we can regroup the equation. On the left hand side, we have the time derivative of the divergence of D minus the time derivative of surface charge density must equal to 0. And here we use another technique. We use another relationship, that is the continuity equation. It says the divergence of the divergence of current density J must equals to the negative of the time derivative of charge density low. So we replace the divergence of J with time derivative of charge density low. So if you regroup if you take the time derivative on the outside and reorder the equation, you end up with the divergence of D equals to the charge density electrical charge density at that point. So it says if you have a standalone electrical charge, then at that point the divergence of electrical flux density must be non-zero, which means you can have standalone electrical charge, and this is also referred as the Gauss's law of electrical field. So on this side you can see with some substitution of continuity equation, you can see that the Ampere-Secchio law is somehow related to the Gauss's law of electrical field. Okay, in the next following four slides, we try to verify the continuity equation. That is, the divergence of J must equal to the negative of time derivative of charge density. So we begin with comments. Okay, so we have conducting wires, and are electrical charge flowing it due to, say, electrical potential due to voltage difference. So we have electrical charge moving at the speed of v. That is, the v is the charge moving density, and the cross-section area of the wire is delta s, and where n is the normal direction of the cross-section area. So the electrical charge density can be described as delta Q over delta V, where the delta V refers to the volume of all where all charge resides. And the charges that cross the surface delta S in time interval delta T can be computed as the product of charge density low EV times the charge drift velocity, the charge moving velocity, times the time interval delta T and the cross-section area delta S. So V delta T times delta S is actually the volume of the space where those electrical charge reside. And thus, we regroup this equation to say that the charges that cross the surface in unit time interval, which is equivalent to current. So we can replace the product of low and V as charge current density J, and the product of current density J with the cross-section area delta S equals to the amount of the total current that flowing in the wire, which can also be expressed as the surface integral of current density J. Okay, then we have the relationship of total current I equals to the surface charge density. If we are looking to a closed space, a closed volume, then the total currents flow in and flowing out. The total current flowing out. I'm sorry. So here we have the surface integral, closed form, closed surface integral. So if either is a positive value, then we have current flowing out of the closed surface. Okay, so this represents the total currents flowing out of this closed surface. That shall be equal to the negative of the time derivative of total charge within that volume. Okay, because you have current flowing out means the charge within this volume, within this closed surface, is decreasing. So that's the reason why you have a negative number. Okay, so current passing through an arbitrary shaped closed surface will equals to the negative of the time rate of charge, of the change of charge, and the total charge within that space, within that closed surface, can be expressed as the volume integral of charge density. So we have two terms, A and B, and we have another relationship is the so-called, we can use the divergence theorem. Divergence theorem states that the volume integral of the divergence of the vector equals to the closed surface integral, which means that we can replace closed surface integral, which is usually more difficult to process, with the volume integral of the divergence of that particular vector. Okay, and the relationship C says what? Says that the divergence of J, that is the current density flowing out of a particular space, can be expressed as the closed surface integral of J with a very small volume。也就是说，电流密度的散度所以左边是电流密度的散度，即为该点流出的电流总和。Okay, we have A, B, C, three relationships, and we try to put them together. Okay, so here we have this, the volume integral of the divergence of J plus the time derivative of total volume charge density of the volume integral of charge density must equal to 0, and you change the order of the two terms. You have this relationship, and you can take the you can put because both sides are comes with the volume integral, so you can put everything in the same space. So here you have the divergence of J plus the time derivative of rho, and then take the volume integral. It must goes to 0, so you can take the volume integral out, and you end up with the continuity equation. That is the divergence of charge density, divergence of surface current, divergence of current density J equals to the negative of the time derivative of charge density rho. Okay. So here let's review and summarize the Maxwell equation. So the first one is the Verdi laws. It says that the curl of E equals to the negative of time derivative of magnetic flux density. So it says that the time variant magnetic field induce spatial variation of electrical field. Okay, so remember, on the left hand side is the spatial derivative. On the right hand side you have the time derivative and the source condition. So check up with the two sentences in red. You have J here and rho here. The two are the source of electrical and magnetic field. To be specific, the current density J is related to magnetic field, as you can see in Ampere circuitial law. The presence of current J induce magnetic field, and the presence of electrical charge density rho induce electrical field. So the second equation is the Ampere circuitial law. You see the time variant electrical field induce spatial variation of magnetic field. And so magnetic field can be produced by the presence of electrical charge. Also, it can be produced by time variant electrical field. So that's the reason why the second term is referred as the displacement current. It's not a real current, but it's equivalent. The effect of it is equivalent to current. That's the reason why they are put in the same part as the current density J. And next, we have the divergence relationships. They are referred as the Gauss's law of electrical field and magnetic field. We have standalone electrical charge. So electrical charge is the direct origin, direct source of electrical field. And unfortunately, we don't have standalone magnetic charge. So the divergence of B always equal to 0. There's no standalone magnetic charge. And the very last part is the continuity equation, as we have seen in the previous slides, which is this is also an important relationship. It tells us the change of charge density is equivalent, is the same as the flow of electrical current. So the divergence of J is related to the time derivative of electrical charge density.